So it turns out, we're doing Chapter 8.2 now, Intro to Logarithms. It turns out that solving exponential functions is not an obvious task. 2 to the x equals 12. Well, we know that's going to be true for some number of x, because 2 to the third is 8, and 2 to the fourth is 16. So for something in between, 2 to the 3.4 or something, we're going to get 12. If you think about the graph of 2 to the x, the graph of 2 to the x definitely hits 12 somewhere. The question is where? How do you solve that equation? If it was x squared equals 12, the solving is pretty simple. You just square root both sides, and you get that x equals plus or minus root 12, which is 2 root 3. But when it's 2 to the x, you can't just take an xth root of both sides. That doesn't mean anything useful to us. And we can't divide by 2, because 2 to the x divided by 2 isn't x. 2 to the x divided by 2 is 2 to the x minus 1. That still doesn't help us at all. So this is a non-obvious task right now. Well, we can solve exponential equations with a tool, with an L, a tool called logarithms. Here, over on this part here, this little table, is how people used to solve exponential problems. This is a table of logarithms for power of tens. Okay, 10 to the x is called a common logarithm. So here's how this would work. Let's say we had the question 10 to some power equals 2.64. Our chart, and we'd say, okay, here's 2.6 and here's 4. So this right here is 2.64. This is saying at this point 10 to the 0.4216 equals 10.64. Or no, 2.64. And they wrote down every single power of 10 they could find. Okay, so people a long time ago just wrote out all the powers of 10 to the x. They had 10 to the 0.1, to the 0.11, 10 to the 0.12. And they wrote all of them down, and they wrote them in this log, this collection of all these powers. Well, if we check 10 to the 0.4216, we get that 2.64 that we were looking for. 2.6399 is that 2.64. So they had all of these things charted down and listed. And so we could use this chart to solve any 10 to the power of something question. That might not seem too useful because it doesn't help us with our problem of 2 to the x equals 12, but I'll show you what they can do. Now we're going to just have to kind of learn some basics about logarithms and exponentials, and one thing to understand is that there's two ways of writing exponential relationships. We are used to the form b to the x equals a. What we're less familiar with is the equivalent form log base b of a to the x. So for example, if I had 3 to the second equals 9, that is written in exponential form. Well, exponential form. In log form, that's log base 3 of 9 equals 2. We can convert between the two forms. So the base of this exponential here is called the base of this logarithm. This is read as log base 3 of 9 equals 2. The power here is the power out here. What you're going to hear me say a lot is that logs are exponents. They're also inverses of exponents. Logs are the inverses of exponentials. But if they're inverses, that means they're the same function, just the opposite direction. So logs are exponentials. That's what that says, trust me. So let's do another example. If I have 4 to the negative 2, that equals 1 over 16. Well, in log form, that would be log base 4 of 1 over 16, and you get out negative 2. This can go in both directions, which is actually pretty useful. We can have log base 2 of 8, and that equals 3. And this is sometimes called the heart thing, where you have 2 to the third equals 8. It's 2 to the third equals 8. And if we had log base 10 of 100, well, that equals 2. Why? Because 10 to the second is 100, 10 to the second is 100. Whenever you have a log of base 10, we don't write the 10. We just call that log. Because in that chart we looked at in the last period, it was all powers of 10. This is called the common log. The common log is when you have a log of base 10. We don't actually write the power. So I could just say log of 1,000. And I know that's 3, because there's a 10 here, and 10 to the third is 1,000. So that's converting between exponential and logarithm forms. It's extremely useful and very helpful. A lot of problems can be solved just by doing that. So let's practice evaluating logarithms, meaning finding their values and without a calculator or table. Think of these all as a question. It's asking the question 3 to what power equals 9, and that power is 2. So log base 3 of 9 is 2. So log base 2 of 8 is 3, because 2 to the third equals 8. What you can do if you're stuck is you can just say it equals x, right? Like we know this equals something, we're just not sure what it is yet, so put an x there. And then you can think, okay, 5 to some power is 1 over 125. Convert to exponential form. What is that power? Oh, it's negative 2. 5 to the negative 2 is 1 over 25. So 1/3 to what power is 27? That power is negative 3. There's a nice little trick. If the base is less than 1, but the input there is greater than 1, or vice versa, if the base is greater than 1 and the input is less than 1, if you switch from bigger to smaller than 1 or smaller to bigger than 1, your results, the power, will always be negative. These are both less than 1, so it's not going to be negative, it's going to be positive. 1/4 to what power is 1/64? You've got to get to the point where you know that that's 3. So this would come out to 3. And just think 4 to what power? Think of this as a power of 4. 4 to what power is 64? Finally, 5 to power is 0. No power. That's impossible. 5 to some power can't equal 0. If you think about the graph of 5 to the x, 5 to the x has an asymptote at 0. It doesn't ever actually touch it, so that never happens. Okay, so a logarithm gives an answer to exponential questions. Think of it that way. So a logarithm is an inverse of an exponent, but if you have the expression log base 4 of 16, that's really asking and then answering the question 4 to what power equals 16. Because if you convert, you get 4 to what power equals 16. Well, that's 2, so in this case log base 4 of 16 is 2. So when you have something in exponential form, 4 to the x equals 20, that's asking the question 4 to what power equals 20. We can convert that to logarithm form and state log base 4 of 20 equals x, and that asks the same question. This is asking the question 4 to what power equals 20. A logarithm is asking the question 4 to what power equals 20. But notice how that converting moved the x. Before, the x was stuck inside this power up here and we couldn't solve anything. When you get something into log form, suddenly the x is all by itself, and if we can just calculate, find log base 4 of 20, we get the answer. Now, we don't necessarily know how to do that yet, but I'll show you pretty quick here how to do that. But the key here is that logarithms are the inverses of exponentials because they're used to solve for x. They undo the power with the logarithm. Again, this is fun and all, but might not seem that useful because how does this help us solve this? Well, if I convert this into log form, I get log base 2 of 12. That equals x. Well, now I have the x by itself. I'm going to cheat and show you something that I don't usually show students for several more lessons, but I want to show you how to get your calculator to do things that aren't just base 12. So your calculator is set to do base 10. If I do the log of 100, kind of looks better. If I do the log of 100 in my calculator, it's going to give me 2 because the calculator does base 10. A trick, though, is if I take this and write it like this, as the log of 12 divided by the log of 2, and do that in my calculator, here, log of 12 divided by the log of 2, it gets me that 3.585 that we saw at the beginning of the chapter. This is saying 2 to that power, 2 to the power of my previous answer gets me 12. This is called the change of base formula, and we'll look at it more. You also might have a fancy enough calculator where if you press the math button here and scroll upwards, you have something here that says log base. I don't. Mine's not fancy enough, which is kind of surprising to me. Here's our recap. We are really just starting to scratch the surface with logs and have a lot more to learn about them. Just know that they're inverses of exponentials. A logarithm of base 10 is called the common log and is written without a base, so this and this are the same. They both equal 2. Each exponential relationship can be written in two forms, exponential form or log form. Thank you so much for watching. I hope you enjoyed it as much as I did, which I'm sure you did because it's a video about math, and how could we not enjoy that? If you found it helpful, please subscribe, please like it, please share it. If you're taking my class, you've got a video quiz about this, so go do that. If you're not taking my class, then congrats, you've avoided having me as a teacher, and that is a real win for you. And comment below if there's anything that I did wrong, or you have questions about, or you could improve upon. And then we'll just spend the rest of the time stalling as we watch this little spirograph go around and around, mesmerizing all of us. And if I were really smart, I'd find some way to, like, hypnotize you and profit off this and say, send me your credit card information or something. So do that. Almost done. 2 more. Pop, pop, pop. Yeah, now it's complete. And then it just starts kind of thickening. You could watch this all day. I'm going to not let you do that.